Okay, I want to go over how to graph systems of equations using technology, using a graphing calculator. You could obviously hand graph these, but the graphical method is made for technology. And it's really where it shows its strength is the crazy long ones. You'll get like the real life ones where you have these really intense, lots of decimals and things like that. That's when it's very, very useful. So you can see here, I've done this is nice, but this is Desmos, and Desmos is a free app for your phone as well as on the computer. And I like it because it's big and I can see it. The TI is great. I use the TI a lot, but if you don't have a graphing calculator, obviously you're not going to buy one just for this. Plus, it's a really tiny screen. I have to squint at it. So when you're using this, simply plug in the two equations. You don't have to rewrite them into point slope or anything. Literally write them as they're listed. With the equal signs and everything, they're fine in any format. And then you're just looking for where they connect. The solution, the answer, would be the point 2, 1. That's all there is. Now, there are three options when you solve a solution. When you solve a system of equations. I speak English, I promise. Actually, I only really speak English. So you can have a case like this where they meet in one point and any linear equations. Now, there are examples where you could have more than one if they were nonlinear, but we're not going to go there. But obviously, you can think if that exists, like just for funsy here, just so you can kind of think about it. Something like this. This is a parabola, right? It's quadratic. This would have two solutions because it hits 2. So it is totally possible. It's just for linear, which is what we're working on, you only ever have one. The other solution that you might see is that there is no solution. So for instance, x plus 3y equals 5. No. There we go. Okay, so parallel lines. I was doing it in my head, and that's my mistakes. Parallel lines, meaning the slopes are the same. In this case, the slopes are both 1/2. Actually, it'd be negative 1/2. Yeah, because it's going down. Anyways, because they have the same slope, they're never going to meet. They're just kind of, they're parallel lines. They're running side by side forever and ever and ever. Okay, so this is a no solution. This is what a no solution looks like, which just means that they never interact. It also can happen in a nonlinear. So if I did something like y equals negative, something like this is a parabola going down. You can see here, this is never going to meet much for the same reason. It's just in the wrong place. It's kind of out of there. So, I mean, there's plenty of solutions where that would happen. Now, the other solution is that they're the same line. So you can see here, I just end up with one line. Well, it says the red line's graphed, but it's right there under the green line because they're the same line. So although these look to me, you can see this I just multiplied by a factor of 2, but this is just that it's the same thing. And you can think about this all the time. It's just something they're reducing. The difference between 1/2 and 2/4. It's the same thing, just one's reduced and one's not. So this also happens. So when you see those, they called infinitely real, infinitely many solutions, all reals, any of those. The book uses the term dependent, which means that they're the same. So they use the term dependent. They also use the term for no solution inconsistent. So inconsistent means no solution. Dependent means all reals. And it really, any term is fine. It's whatever works for you. It's just helpful to understand what other terms exist out there. So when you see it in some random place, you know what it means. So hopefully this helps you visualize a little bit. The point of this section really is that visualization to understand what's happening and what we're looking for. We're looking for that intersection point.